Let's talk about beta decay. Beta decay, like other forms of radioactive decay, happens in the nucleus of an atom here. And during beta decay, what happens is that one of these neutrons that's hanging out in the nucleus, it turns into a proton. Yeah, believe it or not, that's actually possible. Neutrons and protons can turn into each other under certain circumstances. And so in beta decay, you have a neutron and it turns into a proton. And this process of a neutron turning into a proton makes a new electron for the atom. But it's not just any kind of electron. It's a fast-moving electron that gets shot out of the atom super fast. And we call these fast-moving electrons that are shooting out of the atom, we call them beta particles. And that's what these lines here that I've drawn on this diagram are supposed to represent. This electron is shooting really fast, so we call it a beta particle. Even though it's just an electron, it's an electron that's shooting really fast. Okay. So why would an atom want to do beta decay in the first place? Well, as we said earlier, atoms do radioactive decay because there is something about their lives, there's something about themselves that they don't like. They're unhappy, or we could call that unstable. And so for an atom that wants to do beta decay, they have too many neutrons in their nucleus and not enough protons. That's what's making them unhappy. And so by doing beta decay, they can lower the number of neutrons they have, which is what they want to do, and they can increase the number of protons. So after they do that process, they'll become happier, or to sound more scientific about it, they'll become more stable. Okay? So that is an overview of beta decay. Now let's look at how we write nuclear equations for beta decay processes. So we want to know what happens when carbon-14 here undergoes beta decay. You'll see that whenever we do these nuclear kind of problems, the atoms are always written in what we call isotope notation here. So there's a letter, and that represents the element that we're dealing with. So here it's C, so that's carbon. And then there are two numbers to the side. There's a lower number here, and that represents the atomic number, which is the number of protons. And then the number up here is the mass number, which is the number of protons and neutrons. We need to know both of these to figure out what we get after a radioactive decay event happens. So, let's start out by figuring out the number of protons and neutrons in this atom. The number of protons is easy because that's the atomic number, and we can just get that here. It's 6, number of protons. Number of neutrons here. How am I going to get that? This number up here, 14, it's not the number of neutrons, but it is a number of protons and neutrons added together. So if I want to know the number of neutrons, I can take the number of protons and subtract it from the mass number. And that's going to give me 8 for the number of neutrons. Okay. Now let's look at what I'm going to get after beta decay happens. What do we say happens in beta decay? It's that a neutron turns into a proton. So that means that after this happens, I started with 8 neutrons, now I'm going to end up with 7 neutrons, okay? But I get a new proton, because that's what the neutron turned into. So I used to have 6 protons, now I have 7 protons. So let's write this. First of all, I need to realize that my carbon turned into a new element when this decay process happened. Why is that? It's because the number of protons determine what kind of an element you have. So here I had 6 protons, that made it carbon. But now that I have 7 protons, that's going to make it a different kind of element. So what you need to do is look on the periodic table and find out which element has 7 protons. It turns out that it's nitrogen here. So that's the symbol that I want to use, is N. Now, number of protons, I use that as my atomic number, that number goes there. And then I add up the number of protons and neutrons, and I get 14, and there's my mass number. Now I don't want to forget about the electron that shoots out, the beta particle. There are 2 different ways to write the beta particle. One of them is like this. This is a Greek letter beta, and you write 0 there, and then -1. But you can also realize that the beta particle is just another word for an electron. So sometimes people like to write just an e, a lowercase e, -1, 0. And so those are the two ways that you can write the beta particle. Both of them are fine. Check with your teacher or whatever and see how they want you to do it. Okay. Now let's look at another problem that's a little bit different. And what's different about this problem is we won't know what we're starting with, and we have to figure it out based on what we get. So we have some sort of mystery element that undergoes beta decay, and then what we end up with is an atom of sulfur 32, as well as, since we know it's beta decay, we get a beta particle. So what did we start with? Well, let's look at the number of neutrons and protons in this atom. Sulfur has an atomic number of 16, so that's the number of protons that we have. What about the number of neutrons? We can do the mass number minus 16, and that's going to give us 16 neutrons. Okay? So, what did we start with here? What did we have before the beta decay happened? Well, again, in beta decay, a neutron turned into a proton. So before beta decay happened, we had one more neutron. So I had 17 neutrons. And since this neutron turned into a proton, before beta decay, I had one fewer proton. So I had 15 protons over here. Let's write the symbol for this element. I have 15 protons here. So it's going to be a different element than sulfur, which has 16 protons. So when I look on the periodic table, I see that phosphorus has an atomic number of 15. So you can get a P here for phosphorus. And then number of protons is 15, that's the atomic number. And then I add them up, 15 and 17, and you get 32. So let's look at what's actually going on here with the changes in atomic number and mass number. So since we're getting one more proton when beta decay happens, my atomic number is increasing by 1. In this example, I went from 15 to 16. But my mass number stays the same. And that's because we have one less neutron, but then it turned into a proton. So I don't have a new number of neutrons and protons together. So the mass number, which is represented by the uppercase letter A, mass number doesn't change. There's a 0 change there, but Z, which stands for the atomic number, goes up 1. Let's use this so that we can solve these problems quicker, instead of having to always calculate the number of neutrons and protons in each atom. So I'll do 2 more examples, and we'll use this information here as a sort of shortcut to do the problems faster. I'm going to take iodine 131 and write the beta decay equation for that. I know based on what we've learned that the atomic number is going to increase by 1. So I'm going to go from 53 to 54. But the mass number is going to stay the same. So I'm going to stay with 131. All I need to know now is what symbol I should put here. What element did it change into when it got one more proton? Turns out that it turned into xenon, which has an atomic number of 54. So Xe there. And then to write the complete decay, you also want to include your beta symbol or your electron symbol, whatever your teacher wants you to do. Okay? Let's do one more. That's kind of the reverse approach. We're starting with something, we don't know what it is, and it decays and gives us cobalt 52 as well as a beta particle. So, before this process started, the atomic number was 1 lower, right? Because during beta decay it increases by 1. So it was 1 lower when that proton was still a neutron. So 26 protons we started out with, but the mass number doesn't change. So we have 52 up here. What is the element that has an atomic number of 26? Turns out that it's iron. Fe. So that's what I started with here. Now this was beta decay. Sometimes people call it beta minus decay. Beta decay has a closely related cousin called positron decay, which is sometimes referred to as beta plus decay. So if you feel good about this beta minus decay stuff, you'll probably want to check out the video on positron decay to keep going.